How's it going, ladies and gentlemen? Mr. Nani here again, looking at 17.3 acid-base titration. First question, it says 25 milliliter sample of a solution of an unknown compound is titrated with 0.115 molar NaOH solution. The titration curve above was obtained. The unknown concentration is either strong or weak, acid or base. Circle the correct options. Well, let's take a look. The first thing that's going to give something away is where we're starting pH-wise. We're starting at a pH of 3, which means it's got to be an acid. Right, we're starting in an acidic pH range, so we know it's an acid. So is it strong or weak? Well, we know it's being titrated. A strong acid being titrated starts low and then has a really sharp curve towards the equivalence point and then levels back off. The weaker we get, the more flattened out it kind of becomes. And if you take a look at this, it's pretty flattened out, so it's indicating that it's probably a weak one. And if you take a look, it's kind of hard to tell, but it looks like its pH at the equivalence point is about 8. So it being greater than 7 indicates that, hey, the acid's probably a weak acid. So this one is definitely weak acid. Now, if you take a look at number 2, it says pH of a solution prepared by mixing 100 milliliters of 0.25 molar KOH and 100 milliliters of 0.25 molar HCl is blank. Well, hopefully you realize that that is a strong base and that that is a strong acid, and you are mixing equal concentrations and equal volumes. So the acid equals the base. When does that happen? pH of 7. So that's that. 3. How many milliliters of 0.0650 molar NaOH are required to titrate 25 milliliters of 0.0520 molar HBr to the equivalence point? So the equivalence point is where the H plus equals the OH minus. So where does the H plus comes from? It comes from the HBr. All right, well, if we want to know how many H plus we got to figure out, well, how many moles of HBr do we have? So that would just simply be the molarity of that acid times the volume of that acid, right? And we get one H from each HBr, so piece of cake. So we get, all right, well, where does the OH minus come from? It comes from the NaOH. So how do we get moles of moles of OH? You look at moles of NaOH, which is again going to be the molarity of the base times the volume of the base, and they're asking for volume. They give us the molarity. They give us the molarity of the acid and the volume of the acid. So we got to get VB by itself. So this is just some algebra. It's going to be molarity of the acid times the volume of the acid over the molarity of the base. Now, we get one H plus and one OH minus, so we know it's going to be a 1-to-1. We don't have to account for any of that issue. So now it's a plug and chug. Molarity of the acid, 0.0520 times 25 milliliters, all over the molarity of the base, which is 0.0650. And we're going to get our final answer in milliliters when we do this of 20. 20 milliliters, right? Units, that was molarity, this was molarity, this was milliliters. Molarity cancels out, and we're left with the unit of milliliters. 4. It says a 25 milliliter sample of 0.623 molar HClO4 is titrated with 0.37 molar KOH solution. What is the H3O plus concentration after the addition of 80 milliliters of KOH? Okay, so the first thing that we're probably going to want to do is figure out how many moles of each thing we got. So let's start with, what's our, where are you going? Here we are, moles of the base. Well, we got to find the base that we're talking about. Here we go. And we got 80 milliliters of it. So moles of the base is going to be the molarity of the base, 0.37 times the volume, 0.0800. And that equals 0.0296 moles of the base. So the big idea that we're going to do is we mix some acid and we mix some base. We got to figure out, all right, well, how much of what is left over? Did I have more acid? Do I have H plus left over? Or did I have more base and have more OH minus left over to figure out, well, what is the H3O plus concentration? So I got to figure out, well, how much of each thing did I have? So that's the moles of the base. Moles of the acid is going to equal the volume of the acid. Ooh, I have an eraser. Use the eraser, stupid. All right. So we got volume 0.0250 of the acid times the molarity of the acid, which is 0.623. And that tells me I got 0.0156 moles of the acid. All right, well, I can see right away that I got more base than I do acid. So let me see how much base I'm left over with, because these things are going to neutralize each other, and I'm going to be left with extra base. So I'm going to do a subtraction right here to figure out Well, how much OH minus am I going to get? I got 0.0140 moles of base left, right? All right, well, it wants to know H3O plus concentration, and I just found the OH minus concentration. Interesting. So how do I get from OH minus to H3O plus? Well, I know that Kw has to equal the H plus concentration times the OH minus concentration, and Kw at room temperature is always the same. So I'm solving for H plus, do a little algebra. It's going to be Kw over concentration of OH minus equals the H plus concentration. So I'm going to plug that in. I got 10 to the minus 14 all over my 0.0140 moles, right? But I don't have the molarity yet. I just got the moles. So I got to divide by the volume of my solution, which was 25 milliliters plus 80. So I got 105 milliliters, which is 0.105 liters. So now when I plug that in, I should get my final answer of 7.49 times 10 to the minus 14. So that's my answer for 4. 5. The pH of a solution prepared by mixing 50 milliliters of 0.125 molar KOH and 50 milliliters of 0.125 molar HCl. Oh my god, I just heard the same numbers like right next to each other. So let's take a look at this. I got a strong base, I got a strong acid, I got 50 milliliters, 0.125 molar, 0.125 molar. So I got the same amount of acid as a new base. All right, well, when does that happen? Just like in that earlier problem, when we got a pH of 7. Piece of cake. 6. It says a 50 milliliter sample of 0.25 molar hydrozoic acid is titrated with 0.25 molar NaOH solution. What is the pH at the equivalence point? So remember, equivalence point is where the acid equals the base. But here we have a weak acid, so it's not going to be a pH of 7 because it's a weak acid. If it was a strong acid, strong base, then yeah, it'd be pH 7. But that's not what we got. So basically what's happening, we're starting with the anion of the acid. All right, so I'm just going to call that A minus. We're starting with that anion. They give us the Ka, but this anion is going to act as a base. So I don't want Ka, I want Kb. So we got to go, all right, well, how do I get Ka and Kb? Well, we know Kw equals Ka times Kb. So to get Kb, we do divide each Kw by Ka. And we get the Kb of, write that, 2.22 times 10 to the minus 11. When we plug in the Ka and the Kw is 10 to the minus 14. So now what? Well, that anion is acting as a base, you know? So what's happening is it's attacking the water. It's making the acid and the OH minus from that. So this H2O is a liquid, so it's going to drop out of our Kb expression. So we're going to be left with Kb expression being as such. So now the question becomes, well, what do I do with that? All right, well, we got to figure some stuff out. If I had if I started with, I got to figure out how much A minus I got, right? Because it's, right now I titrated it and I got 50 milliliters of that much stuff. So I got to figure out, well, you know, what's my molarity of my acid, or, you know, my A minus? Well, that's going to be the 0.050 liters times the 0.250 molar, and that's going to give me my moles of my acid, which I found somewhere. Hang with me for a second. Oh, I totally lied. You know what's easy about this? 50 milliliters and, well, same concentration. So I added more. I added 50 milliliters of base to it. So the concentration of the hydrozoic acid is basically cut in half. So I know that the concentration of A minus is going to be equal to 0.125, half of the acid concentration that I started with. All right. So now I got that. Now it's an icebox question problem. So let me make some room. All right, so I got A minus, started with 0.125 molar. H2O drops out, HA, I started with 0, and OH minus, I started with 0 as well. Now, a certain amount of this is going to get used up, and it's going to make the same amount of HA and OH minus. All right, so now I have my equilibrium constant, my equilibrium values of 0.125 minus X, X, and X. And I'm going to clear up some room up here. All right, so now I got to plug this in to that equation, and I'm going to end up with x squared over 0.125 minus x. Right? So now I got to do the whole quadratic thing. All right, making more room down here. Doopy doopy doop. So I'm not a fan of showing all this algebra because it's just algebra. So we get x squared plus kb x minus 0.125 times kb. So now I can plug and chug and get my value for x, which is what again? My OH minus concentration. And I get x equal to 1.67 times 10 to the minus 6. And now I'm not done because what it's asking is pH, right? So how do I get pH from that? Well, there's a couple of ways. The easiest way for me is to get the POH. Remember that pH plus POH has to equal 14. So if I'm trying to solve for pH, it equals 14 minus the POH. And the POH is just negative log of this stuff. So I plug it in, 14 minus negative log of that number, 1.67, either negative 6, and I get final answer 8.22. So you know what? Let me kind of try to boil it down to what just happened. All right. First, all the acid was neutralized, which means that we had the conjugate base, which is a strong base because the acid we started with was a weak acid. All right, so now we got this strong base anion floating around reacting with water, right? So it's acting like a base. So we got to use the Kb to get how much OH minus concentration there was. And once you have that, you have to, depending on what path you want to take, you got to go from the OH minus to the pH. All right, you can go a couple of routes. You can go OH minus to what's my H plus concentration and get pH, or you can go, well, I know OH minus, so let me figure out my POH, and from that get pH. Right? Either way would work. But that's your final answer down there. Kind of an ugly problem. What are you going to do? 7. How many milliliters of 0.24 molar NaOH are required to titrate 100 milliliters of 0.012 molar butanoic acid to the equivalence point? So equivalence point again is where acid equals the base, right? The H plus equals the OH minus. So what's with this Ka stuff? It's extra. It's a red herring. It's just to throw you off. It's simply a Mavab thing. So how many H pluses do you get from that acid times the molarity and volume of the acid should equal the number of OH minuses you get from the formula times the molarity of that base times the volume of that base. All right, so now let's figure it out. We got 0.24 molar. Well, that's our MOB. So 0.240 molar. Required to titrate 100 milliliters of that. So we're talking about the acid over here. 100 milliliters. And 0.12102 molar. And we get 1 H plus from that. We get 1 OH minus. So we're trying to solve for VOB. So you divide each side by 1 times 0.240. Get rid of that. And you end up with VB, the volume of the base needed, to equal 42.5 milliliters. One more. Then I'm taking a break. Something how to live my life. 50 milliliter sample of 0.650 molar hydrozoic acid is titrated with 20.5 milliliters of 0.25 molar NaOH solution. What is the pH? Gives you the Ka. So first question is, all right, well, which one do I have more acid or more base? And to figure that out, you got to go, all right, well, let me compare moles of the acid, which would be 0.050 liters, right, from here, times the molarity of the acid, which equals 0.0325. And now I got to do the same thing for the base. Equals the volume of the base, 0.0205 liters times 0.250 molar, which equals 0.005125 moles of the base. And this was moles of the acid. So now the question is, which one do I have more of? Well, I have more acid. So I'm going to go, well, how much acid do I have after I add that much base? So I got to do a subtraction right here. I end up with 0.0274 moles of acid. Now, if I want to get pH, I got to get H+. I found how much of the acid I got, and I know how much base I got. Well, let me convert these into molar, right? So if that's how much acid I got to now divide it by the volume of the whole thing. Now I had 20.5 milliliters and I had 50 milliliters combined. So my new volume is 0.0705 liters. So my molarity of the acid is 0.388. All right, and what about my molarity of the base? Well, this is how much base I have. Right, I have 0.005125 moles. Divide that by the new volume of 0.0705 liters, and I get molarity of my base to be 0.0727 molar for my base, and that's molar for my acid. So I got Ka, I got molarity of acid, molarity of base, and it's asking for pH, and there's a formula I know that has all those things. Right? The Henderson-Hasselbalch equation. So now I'm just plugging and chugging. All right, pKa is the negative log of the Ka, which is 1.9 times 10 to the minus 5, plus the log of the amount of base, which I got up here, 0.0727, all over the molarity of the acid, 0.388, and that is going to equal 3.99. That's it. I know, a lot of confusing stuff, right? So basically, you gotta break it down, draw a picture if you need to, figure out what's going on. So I added acid and base. So the question is, which one do I got more? You know, who wins? Is it the acid greater than the base, or vice versa? Or is the base greater than the acid? You got to figure that stuff out so that you can then go, all right, well, what's going to happen? So after I mix them, acid left and base left. How much of each thing do you have? And then you can go, all right, well, once I know that, I can do the Henderson-Hasselbalch equation. and get your answer. Fun. I'm tired. I'm taking a break.